We as people have forever been enthralled by the limitlessness of the universe, continually addressing whether we are genuinely the main wise species in presence. For quite a long time we have focused on the sky, contemplating the presence of different universes, thinking about existence past our home on the planet, and contemplating whether different civic establishments may be out there. This chance has now become more unmistakable than any other time in recent memory. NASA's executive has as of late uncovered that the James Webb Space Telescope JWST has caught something unprecedented at the edge of our enormous area. The telescope has concentrated on Proxima B, an exoplanet found somewhat near us that might have conditions reasonable for life. Proof has been assembled proposing that a city-like construction could exist on a superficial level, possibly made by clever creatures, an idea that has stayed speculative as yet. NASA's new discoveries have shown that fake lighting on Proxima B has been distinguished, flagging a significant revelation. Besides, the manufactured piece of its air has additionally been recognized, recommending the chance of life on this far-off planet. The JWST, using its trend-setting innovation, might have identified life on Proxima B, an exoplanet found 4.14 light-years from Earth. Proxima B has attracted a lot of consideration because of its capability to help life circling around the star Proxima Centauri, a red bantam, a lot more modest and cooler than our Sun. Proxima B was found in 2016. It is arranged in the tenable zone or Goldilocks zone around its star, where conditions could permit fluid water, a fundamental part for life as far as we might be concerned to exist. This one-of-a-kind situating has produced extensive premium, as the chance of it having the option to help life stays a hotly debated issue for hypothesis. Anyway, it is vital to take note of that. Deciding if an exoplanet can really uphold life is a perplexing riddle with various variables to consider. Proxima B is around 1.3 times the mass of Earth and finishes one circle around its parent star in roughly 11 Earth days. Anyway, regardless of these Earth-like elements, it isn't destined to be an ideal copy of our planet, and we can't just expect that it would be tenable. The decency of Proxima B relies upon different elements, with the planet's air being one of the most urgent. The air fills in as a defensive layer, managing temperatures and cultivating the circumstances expected forever. Anyway, insights concerning Proxima Honeybee's air are as yet unclear, making it trying to conclusively evaluate whether the planet can really uphold life. Specialists using the James Webb Space Telescope are at the front line of investigating distant exoplanets. For example, Proxima B, their tenacious quest for information has driven them to foster imaginative strategies and devices to concentrate on these far-off worlds' climates, with a definitive point of recognizing indications of something going on under the surface past our planetary group. Perhaps of the most impressive instrument in this try is the JWST, which is set to change how we might interpret exoplanets' climates. The telescope's state-of-the-art innovation is intended to test the universe, profoundly disentangling its mysteries and giving a better approach to look for livable universes and indications of extraterrestrial life. A focal objective of the JWST is to zero in on the climates of exoplanets, searching for explicit atoms and biomarkers that could demonstrate the presence of life. To accomplish this, specialists have tweaked their perception techniques utilizing the telescope's unrivaled responsiveness, and Goal 1 procedure includes concentrating on travels where an exoplanet passes before its host star. According to our viewpoint on Earth, during such travels a piece of the star's light goes through the planet's air, permitting cosmologists to dissect the synthesis of that air by inspecting the unearthly characteristics of the light. They can recognize key atoms like water, methane, carbon dioxide, and oxygen, which are frequently connected with life. Among the most charming focuses for identification are biomarker particles, which are synthetic builds that could highlight natural cycles happening on far-off universes. Oxygen, ozone, methane, and smelling salts are instances of such biomarkers, as they have organic beginnings on the planet and could flag the presence of life whenever found somewhere else. The JWST excellent responsiveness and High's ghastly goal permit researchers to distinguish, even follow measures of these biomarkers, offering important experiences into the livability of far-off planets. Furthermore, the telescope's huge opening and long perception times upgrade its capacity to catch nitty-gritty travel information. Subsequently, working on the dependability of its discoveries on account of Proxima B, the JWST presents an unmatched chance to concentrate in the world's air and its true capacity for supporting life. As the nearest known exoplanet to Earth, Proxima offers an exceptional subject for definite assessment by examining the light going through its air. Analysts desire to dive deeper into its substance, cosmetics, temperature, design, and environment, all of which assume a critical part in deciding its tenability. The capacity to review exoplanets' climates involving the JWST is a momentous headway as we continued looking for life past our nearby planet group. This capacity addresses a Goliath jump forward in how we might interpret the universe and the potential for life somewhere else. The JWST unmatched capacities permit researchers to investigate the organic and ecological circumstances on far-off planets, possibly upsetting our way to deal with astrobiology and the quest for extraterrestrial knowledge, as well as considering exoplanetary heirs. The JWST will likewise add to how we might interpret more extensive grandiose peculiarities from the development of stars and universes to the advancement of planetary frameworks. One more key calculate deciding if Proxima B could uphold life is the presence of water. Albeit the planet is situated in the livable zone, the accessibility of fluid water on its surface is pivotal for surveying its livability. Water in different structures, for example, seas, lakes, or streams, is fundamental for supporting natural life. Scientists are momentum ly searching for indications of fluid water on Proxima B, as this would be a critical mark of its capability to have life. The presence of water, fume, or ice is additionally critical, as water is a key component for organic cycles. Notwithstanding water, Proxima B's air will likewise be investigated for factors like temperature, pressure, and geographical action. Outrageous circumstances, for example, extraordinary intensity or frigid temperatures, could make endurance unthinkable. Steadiness is one more basic perspective to consider, as volcanic action or seismic developments could disturb tenability. Proxima Honeybee's potential clean locked state, where one side of the planet is consistently in obscurity and the other is constantly enlightened by the star, could prompt temperature limits that would influence its capacity to help life. Further examinations are additionally zeroing in the World Substance Organization, especially searching for natural accumulates like amino acids, which are essential to life. Analysts are looking at whether Proxima B gets sufficient energy from its star or different sources to support natural cycles and advance the development and multiplication of organic entities. Anyway, in spite of these examinations, the inquiry remains: does Proxima B have every one of the fundamental elements for life? Is there authoritative proof to help its livability? The disclosure of Proxima B in 2016 was a striking accomplishment in the field of exoplanet research. Cosmologists utilized the profoundly exact spiral speed strategy using the HARPS instrument to recognize the unobtrusive gravitational shaft of Proxima B around its parent star. Proxima Center. This technique has been instrumental in distinguishing various exoplanets, including Proxima B, because of its capacity to identify little changes in a star range brought about by the gravitational impact of circling planets. HARPS, a high-accuracy spectrograph, works by measure in the spiral speed or Doppler movements of a star which result from the gravitational draw of a circling planet. This method permits space experts to identify even little planets like Proxima B by noticing the wobble in the star's movement. The progress of the HARPS instrument lies in its responsiveness, which permits it to distinguish speed varieties as small as a couple of meters per second. This accuracy is crucial for identifying Earth-sized exoplanets orbiting distant stars. The instrument operates in a controlled environment to minimize thermal fluctuations, ensuring stable and reliable measurements. The data gathered by HARPS is carefully analyzed using advanced algorithms and statistical techniques to extract meaningful information about the properties of exoplanets. In the case of Proxima B, HARPS was fundamental in detecting its presence by tracking the radial velocity of Proxima Centauri, revealing periodic variations that indicated the presence of an orbiting planet. Overall, the discovery of Proxima B marked a significant achievement in exoplanet research, demonstrating the power of precision spectroscopy in uncovering distant worlds. As astronomers continue refining their methods and expanding their search, HARPS will remain at the forefront of exoplanet detection, helping to answer key questions about the prevalence of life in the universe and the nature of planets beyond our solar system. As scientists continue to refine their techniques and push the boundaries of exoplanet exploration, HARPS remains an essential tool in uncovering the secrets of distant worlds. Its sensitivity and accuracy have not only enabled the discovery of Proxima B but also numerous other exoplanets, each contributing to our growing understanding of the vast diversity of planetary systems throughout the galaxy. As the search for extraterrestrial life intensifies, instruments like HARPS, alongside the revolutionary capabilities of the James Webb Space Telescope, will be crucial in determining whether other planets beyond our solar system can truly support life. In the near future, with continued advancements in technology and observational techniques, astronomers hope to expand their catalog of exoplanets within the habitable zones of their respective stars. The goal is to identify worlds that could have the necessary conditions, such as the presence of liquid water, a stable atmosphere, and the right chemical elements to support life forms similar to those found on Earth, or perhaps even drastically different ones. The study of these distant planets may not only answer questions about Earth's uniqueness but also provide vital insights into how life might arise elsewhere in the universe. The potential habitability of Proxima B represents just one aspect of the broader quest to understand the conditions necessary for life in the cosmos. As researchers refine their models and analyze the growing body of data from telescopes and space observatories, we are likely to witness more discoveries that challenge our assumptions and expand our definitions of what constitutes a habitable planet. Proxima B's proximity to Earth makes it a particularly compelling target for ongoing research, offering the possibility of groundbreaking insights into the nature of life beyond our home planet. Although significant progress has been made, many challenges remain. Determining the exact conditions that make a planet habitable involves numerous variables, and each discovery adds another layer of complexity. The data collected by both the HARPS instrument and the James Webb Space Telescope will continue to guide future missions, inspiring new questions and discoveries in exoplanet research. For example, understanding the composition and structure of Proxima B's atmosphere will require even more sophisticated instruments and techniques, which could lead to the identification of biosignatures hinting at the presence of life. As the investigation into Proxima B continues, scientists are not only focusing on its potential to support life but also on its broader implications for our understanding of planetary systems. For instance, how common are planets like Proxima B in the universe? Could other exoplanets with similar characteristics harbor life, or do we need to search for entirely different conditions? These questions drive researchers to develop new methods for detecting and studying exoplanets, as well as more accurate models for understanding planetary formation and evolution. One critical area of focus is whether Proxima B's atmosphere is capable of maintaining a stable climate over long periods. Climate stability is essential for life to thrive, and without the right atmospheric conditions, any potential for habitability would be limited. The role of a planet's magnetic field is also crucial in this regard, as it protects the atmosphere from being stripped away by stellar winds. Proxima B's close proximity to its star, a red dwarf, means it is exposed to intense radiation, which could pose challenges for the planet's ability to sustain a protective atmosphere. Understanding how Proxima B interacts with its parent star, and whether its atmosphere has endured will be critical in assessing its potential for habitability. Looking ahead, the combination of data from JWST and other advanced telescopes will offer a more complete picture of Proxima B and similar exoplanets. Over time, we may gain the ability to directly detect signs of life, or at least stronger evidence of a planet's ability to support life. The findings from these investigations could reshape our understanding of life in the universe, opening up new possibilities for the existence of extraterrestrial civilizations and even redefining our place in the cosmos. As the study of exoplanets continues to evolve, scientists are increasingly examining the role of stellar environments in shaping planetary habitability. While Proxima B's proximity to its star makes it an excellent candidate for study, it also presents challenges related to its star's activity. Red dwarfs like Proxima Centauri are known to emit intense solar flares, which could potentially strip away the atmospheres of nearby planets. This means that even if Proxima B has the right conditions for liquid water, its atmosphere might not be stable enough to support life long-term. Researchers are therefore focusing not only on the composition of Proxima B's atmosphere, but also on how it interacts with the radiation from its parent star. The potential for life on Proxima B is further complicated by the possibility that the planet is tidally locked. In this scenario, one side of the planet would always face the star while the other remains in permanent darkness. This creates extreme temperature differences, with one side potentially becoming too hot for life while the other remains too cold. If Proxima B is indeed tidally locked, researchers must examine whether a habitable zone might still exist in the planet's twilight region, where conditions could be more moderate. Beyond its star's activity, Proxima B's orbital dynamics and geological history also play a crucial role in determining its ability to maintain a stable climate. For example, volcanic activity could contribute to the planet's atmosphere and potentially create conditions for life. Whether or not Proxima B's surface is geologically active is another important avenue of investigation. New technological advancements, particularly in spectroscopy, are allowing astronomers to study exoplanets in greater detail than ever before. The ability to detect chemical signatures of life in the atmospheres of distant worlds is a game-changer for astrobiology. While Proxima B remains an of the most intriguing candidates, scientists continue to search for new targets of study. Each discovery brings us closer to understanding the broader conditions that make a planet truly habitable. As our tools and techniques continue to improve, our understanding of exoplanets like Proxima B will only deepen. What began as a question about the possibility of life beyond Earth is rapidly becoming a mission to explore and comprehend the complex factors that influence planetary habitability. As we venture further into this exciting field, the search for life beyond our planet is more promising than ever.